base was 10 microampere. So at the emitter.
No, sorry. What are you talking about? What is the unit of voltage?
It will be 10.7.
Voltage at the base is how much?
Uh,
Can you see it there? Can you see the voltage at the base is 1 volt?
yes.
So what will be the voltage at the emitter?
I think we'll add 0.7 to.
Yes, add it. How much?
At the emitter.
Sorry?
So which voltage are you looking for?
Voltage at the emitter, this voltage. Can you see a pointer?
Voltage at the emitter.
Is
It's 1.7, sir. Am I right?
1.7. Voltage at the base is 1 volt. This is a PNP transistor. At the N, you have 1 volt. At the P, if this BJT is conducting, it must be 0.7 volt more. So voltage at the emitter is 1.7 volt. Now, look at that 5 kilo ohm resistance. One end of the 5 kilo ohm resistance will have a 10 volt. Can you see it? The other end of the 5 kilo ohm resistance got a 1.7 volt. Now calculate the emitter current.
So since we have because we want what emitter current, we'll first find the VBE. Am I right? So we're gonna say the voltage at the base and the voltage at the emitter, we minus them together and then we divide them by that resistance.
Why do you want to minus them? You already have voltage at the emitter. That is 1.7.
Yes, we minus it with the 10 volts.
10 minus 1.7 divided by 5K. What's the answer?
Answer is 0.00166 amps. Ampere.
I want the answer in milliamps.
1.6 milliampere.
How much?
It's gonna be 1.6 milliampere.
1.66 milliampere. So you
Yeah.
have the emitter current. Now, do you have the base current? Can you find the base current? IB equals, how do you find the base current from the emitter current? IE divided by beta plus 1. And the value of beta, oh sorry, we don't have the value of beta now, so you can't find out.
Yes.
But you have the emitter current. And you already have the base current. Why? If there is a current coming through 100 kilo ohm, where is that current coming from? If there is 10 microampere going through 100 kilo ohm, where is that current coming from?
Isn't that the base current?
That is the base current. So we already have the base current. We already have the emitter current. Can we find the collector current? IC equals emitter current minus base current. Can we do it like that? That is 1.66 milliampere minus 10 microampere. How much is your collector current?
Is it 1.65?
Yes. So we have base current 10 microampere. We have emitter current 1.66 milliampere. We have collector current 1.65 milliampere. We did find all the currents. What else we need? Find the value of beta. How do you find beta? Beta is IC over IB. Am I right?
Yes, sir.
How much is IC? 1.65 milliampere. How much is IB? 10 microampere. So what is the value of beta?
Is it 165?
165. That is the value of beta. Now we need to work out the value of alpha. Alpha is IC over IE.
Sorry,
IC is 1.65 milliampere. IE is 1.66 milliampere.
sir.
Yes,
What are the units for beta and alpha?
constant.
So they don't have units.
No.
Okay, sir.
The answer for alpha is like 0.99 something, so it's very close to 1.
0. But remember, alpha value will be always close to 1. So you simply write 1. You won't get any mark. You have to represent as an accurate as possible. 0.9940. That is the value of alpha. Now, going back to this problem. Out of all these circuits, we only knew one value, that is Vp equal to 1. Using that value, we found the current through 100K. Remember, Vb is just a voltage that is given to us. So using that, we worked out current through 100 kilo ohm. That is 10 microampere, which is the base current. So through the base, current flowing through 100K to the ground. So that 10 microampere that we got is actually the base current of the PNP transistor. Then, if you have 1 volt at the base, add VBE, you get emitter voltage. Remember, this is a PNP transistor. You have to add the voltage. This arrow indicates direction of current flow. That means if you need to have a current flow in this direction, voltage at the emitter must be more than voltage at the base. That is why when we go across the arrow, you add. When you go through the arrow, you subtract. So this voltage is 1.7. You go through the arrow, you subtract VBE. You get 1. If this voltage is 1, you go across the arrow, opposite direction to the arrow. Then you need to add the voltage. Voltage at the emitter is 1.7. Supply voltage is 10 volt. 10 minus 1.7 over 5K is your emitter current, current through 5 kilo ohm. Emitter current, and there is a base current. Emitter current minus base current is going to be the collector current. Now we know the base current 10 micro, emitter current 1.66 milliampere, and collector current 1.65 milliampere. Now we can work out beta is IC over IP, alpha is IC over IE. The same problem is worked out, and it is, see, I'm just clicking it there. Okay, that you go and watch it when you want. So currently we are moving on. Collector current base VBE, IC versus VBE, characteristics of a BJT. We did an identical one with a diode in forward bias. We put VD on the X and ID on the Y. We found same graph, exponential graph. Or basically, diode characteristics is exactly same on a BJT when you look at VBE versus IC. For the first order analysis, we may use VBE approximately 0.7 volt. If you know a BJT is conducting we can take it for granted VBE is somewhere very close to 0.7 volt as in a diode. VT is, of course, 25 millivolt. We treat it as a constant thermal equivalent voltage. Now we are going to see something called early effect. That is dependence of collector current on collector voltage. This is, we have seen something similar yesterday, VCE versus IC. Now we are seeing the same thing with a bit more detail. Okay, this is the standard name for this kind of a circuit here, this kind of a graph is output characteristics of a BJT. That is VCE versus IC. That is this battery voltage VCE versus IC. Okay, and it is happening at a constant VBE. So VBE at a certain value 0.7 like that, you get this graph. You make VBE slightly bigger, 0.72. Then you get this graph. The third one, make VBE 0.73 or 74. And fourth one, 0.76, something like that. So you get different graph. And if all these graphs got a slight slope, if you put a ruler over the graph and extend the line towards the negative side, all this extension seems to converge at a certain point. And that point is a voltage, and that voltage is called early voltage. Okay. The importance of early voltage is, we originally studied that VCE, the function of VCE is to provide a reverse bias between collector and base. Once you provide the reverse bias, the magnitude doesn't matter. But what we see according to this graph, the magnitude of VCE in fact affect collector current slightly. That is why you get a slope. If VCE should not affect, then you should have been getting a perfectly horizontal line, which we are not getting. Okay, what is the final effect? Effect is very much simple. We may consider the effect of this early voltage when you make a model. We will see that. We studied earlier that we need a reverse bias across collector base junction. The magnitude of it is not important. However, IC, VCE characteristics of a common emitter BJT illustrate that magnitude of VCE has a small influence on collector current. This is due to the base width modulation effect. Okay, forget about that. That is the theoretical background. The effect must be included into the model by placing a finite output resistance R0. Look, it is a very small r with a small suffix 0. That is VA over IC between collector and emitter. We will see. The explanation in words may not be a little too long to capture, but the effect is quite simple. Look at the BJT, base, emitter, collector. In this case, you include that R0 small r, small 0, r naught, which is same as VA divided by IC. You include this. That is the only effect of early effect. Practically speaking, some part of the collector current must be flowing through this. That is the practical effect. But reasonably speaking, this value of this R naught is very high, like 100 kilo ohms. So effect of this early effect is negligible. This is representation of a BJT. There is a base, there is a collector, there is the emitter. This is your VBE 0.7 volt and VCE 0.2. That is, VCE 0.2 means this BJT is in saturation. At saturation, you get a saturation current IC. Base current, collector current is IC sat. That is how we represent it. Okay. Example 4.3. BJT has a beta of 50. Calculate the value of VBB for the following condition. BJT must be in the active mode with the VCE equal to 5 volt. Okay, look at the diagram. We have a VCC of 10, RC of 1K, then we have a BJT. At the emitter, there is no resistance. So this is your VBE. This now the question is, what is the value of VBB so that you get a VCE of 5 volt? Okay, VCE 5 volt means at the collector 5 volt. Okay, look at RC. One end of RC is 10 volt, other end of the RC is 5 volt. You can work out collector current. Somebody please work out, or rather everybody work out the collector current now. IC equals 10 minus 5 divided by RC. That is 5 divided by 1K. That must be 5 milliampere. Are you getting it?
Yes.
So we got collector current of 5 milliampere. Now, what is the value of beta? Given in the question is 50. Now, work out the base current, IB. IB equals IC over beta, which is 5 milliampere divided by 50. How much?
.1, sir.
That is
0.1.
give me that answer in microampere. That is 100 microampere. That is 0.1 milliampere. So we got
100.
100 microampere. That's right. What is the question? Calculate the value of VBB. Calculate the value of VBB so that you get 5 volt here. Right? How do you work out VBB? Let us write a KVL, Kirchhoff's voltage law expression for VBB. VBB must be equals, start from 0. This is the loop that we are doing. Like that. This is VBB minus IB times RB minus VBE equal to 0. Do you agree? VBB minus IB times RB minus VBE equal to 0. Do you agree? Yes. Speak.
Sir, are you writing on the slides now?
No, I can't write anything on the slide. I can't even draw on the slide.
Okay, just wanted to make sure.
I am just showing you. Can you see my pointer?
No.
Oh, that is difficult. I cannot write or draw anything on the screen because D2L decided that I can't use PDF document today. I had to get only the PowerPoint slide. And this is not allowing me to write anything at all.
Okay.
So you can see VBB. Write a Kirchhoff's voltage law expression. VBB minus IB times RB minus VBE equal to 0.
Sir, can you please repeat?
VBB minus IB RB minus VBE equal to 0. I want to know, can you show my hand? Can you see my hand?
Yes, sir.
Yes, sir.
Okay. Let's solve the problem in this way. We have a 10 volt and this is 1K. This is 5 volt. This is VBE. The side positive. This is VBB. The question here is, we found you need 5 volt. So we can find collector current is 10 minus 5 divided by 1K. I hope you can see that. That is 5 milliampere. Base current is collector current divided by beta. That is 5 milliampere divided by 50. What was the answer? Answer was 100 microampere. Next is, we need to make a Kirchhoff's voltage law expression this way. We can write VBB. Remember, current through this is called IB. In fact, we worked it out, 100 micro. This is the Kirchhoff's voltage law expression. This is what we need to find out. Therefore, we can write VBB equals, move this 2 to the other side, is IB RB plus VBE. This is 100 micro times, how much is the value of RB?
Okay, sir.
10K.
Sorry, I can't hear you.
10 kilo ohm.
10K. Hundred micro is 0.1 milli. 10 times 0.1 is 1. This is 1.7 volt. Am I right? You can verify.
Yes.
Sir, can you like move the paper upwards a little bit?
Yes. Are you fine now?
Okay, sir, can I ask a question?
Yes.
If we have the VCE that is given, there is no need for us to literally find the VBE or the VCE.
You mean the VBE?
I was meaning that the VCE. If we don't have the VCE, we have to use the 0.7. if they didn't give us
Are
the
you
VCE.
talking about VCE or
Yes, the VCE?
VCE is given?
Is if it's not given, do we have to use the 0.7
No,
voltages?
no way.
Okay.
VCE has nothing to do with VBE.
Okay, sir.
The value of VCE could be anywhere between 0 up to 10, anywhere. But if VCE equal to 0.2 says saturation.
Sir,
Yes.
can I ask what was the value of VBE?
We only have one value for VBE.
Which is 0.7.
Yes.
Okay, thanks.
So I'm going back to the slide. All right, we reached back to the same slide. In the previous slide, the one before, we found something called first order analysis. This first order analysis means only one thing: easy calculation. Very easy calculation, pen and calculator solving of a problem. That is called first order analysis. Of course, there is a second order analysis, third order analysis, and 10th order analysis as well. Our simulation program is much higher order analysis, even 10 times more than what we could do. So in normal calculation, we are limited to first order analysis. So why there is a first order, second order, third order like that? There is only one point. We are trying to learn electronics. We are not trying to learn maths. So a first order analysis is what we are going to use in most of the problem that we have. All the final detailed verification, you can do it using a simulation program. So basically speaking, we are compromising high levels of accuracy in first order analysis. But if you are practicing electronics, what is more important is this first order analysis. You can always go and use your computer to do the final verification. And if the simulation programs say there is a problem, then we can also verify and accommodate that in our design. So first order analysis is what we are going to do in our study of electronics. Going back to where we came from. BJT circuits at DC, first order analysis. A first order analysis compromises the accuracy for speed and insight of a circuit behavior. Hence, the following assumptions are used. Remember, we need speed. Why we need speed? Because we need a quick understanding of what is happening in the circuit. And I saw a hand somewhere. Please ask your question.
No, sir. I was trying to ask if you are on the same slide as it appears on my PC.
What is appearing on your? What is appearing on your?
BJT in an active mode.
No.
Okay.
This D2L got huge amount of problem. Now mine is resetting and is restarting from zero again. Okay, we reached the point where we missed the link. So we are, okay, this is slide number 36. We need speed, we need something called insight. Insight means by looking at the circuit, you need to get a feel how this is working. That is called the insight. Delay.
Sir, mine is on slide number 10.
Are you using my tutor, D2L?
I logged in using the link.
I don't know whether I must just stop and run away. Okay, you got a PC, right?
Yeah.
What you need to do is open that PowerPoint presentation that I have uploaded. Download it into the PC and keep it there. And each time I move my slide, I can let you know.
Okay.
I think that's the only way forward. because this, I am on slide number 36 now, you don't see that. Okay, with this slide, we can stop for today. And if there is a problem, next one, I want, not yet here. Okay. I want all of you to try this example 4.4 on slide number 38 after today's class, which is going to end soon. Okay. In a first order analysis, we compromises accuracy for speed and insight. We may neglect the early effect. There's nothing wrong in neglecting early effect in usual calculation because we are using discrete components. When you study about integrated circuit and designing integrated circuit using a BJT, you cannot neglect anything. You have to include every bit of theory that you learned. But now we are dealing with discrete components. You may neglect the early effect. VBE approximately 0.7 for a conducting transistor. VCE equal to 0.2 for a saturated transistor. And see, you can see those three lines, red, green, and I can't see the third one below. VBE less than 0.7, IC equal to 0 is cut off. VBE nearly 0.7 and VCE greater than 0.3 is active. And there is one more for saturation. And in between the slide, this band is sitting, I can't move anything here. But you can see it on your side. That is, saturation means VBE will be around 0.7 and your VCE will be less than 0.3. That is 0.2, 0.1, 0. That is saturation region. Now I ask everybody to go and try to work out this problem. It is given, the directions are given on the slide itself. All right, any questions?